A plastic beaker containing 0.1 kilograms of water at 18 degrees Celsius was placed in a refrigerator for 450 seconds. After this time, the temperature of the water was found to be 3 degrees Celsius. The specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. So first thing it's asking us to calculate is the energy transferred from the water. Okay. So this is what I've jotted down. So you can get all this information from the question. Again, just to show you my what each of the symbols and letters mean. Again, this delta change in temperature. It said it goes from 18 to 3 degrees Celsius. So that's obviously going to be my change in temperature there. SHC, again, you can use just C as it is. And for those of you, I'm going to be doing this question with a triangle. So heat transferred or energy transferred, and the C is specific heat capacity, and I'm using delta T as my change in temperature. So the question's asking us for heat transferred. So again, I cover up my E like this. Okay, so I'm left with M times C times delta T. So let me write that down. So delta E is equal to my 0.1. It's already in SI units. Do the specific heat capacity first, 4,200, which is my C, then my change in temperature, which is 15. If you plugged all that in your calculators, okay, you should get 6,300 joules. So 450 seconds is what we haven't used just yet in our answering of question 4, and again, in physics, you've got to make sure you use all the variables, okay? And that's a clue to the question. So rate of transfer of energy, what we mean by rate of energy is how much energy is being transferred per second. So if we're told that in 450 seconds, the temperature goes from 18 degrees Celsius down to 3 degrees Celsius, that's the time it has taken. We've just worked out the energy, total energy transferred, our delta E, and we're given 450 seconds in the question. So all we need to do now is to divide 6,300. Okay, so rate of energy transfer is equal to obviously your delta E, which is what we've just worked out, over delta T. So I'm going to do lowercase t so that you don't get confused with temperature. So it's just basically the energy over the time taken. We've worked out the energy, 6,300 joules in the question, tells us it does this in 450 seconds. So that's joules per seconds if we look at the unit. Again, plug that into your calculator. You should get something close to 14 joules per second. Now I'm going to do part B now. It says, calculate how much more energy would need to be removed from the water to cool it from 3 degrees Celsius and to freeze it. The specific latent heat of fusion of water is 340 kilojoules per kilogram. Now, this question, as you can see, it's 4 marks. This question we need to do, we need to combine formulas. First things first, you need to know at the freezing point of water is 0 degrees Celsius. That's when it becomes solid. So therefore, the change in temperature is going to be 3 minus 0. Okay, that's the bit of additional information or general knowledge you should know to answer this question. So this is B, part I. I now know my delta T is equal to 3 minus 0. Okay, because it goes to freezing point. Next thing, I'm told now it's still water, bear in mind. So this information of the specific heat capacity given to me in 4a is still useful. So I'm going to jot that down on my whiteboard so I know C is still 4,200. That's still applicable to me. Yep, so in 4a, it was going from 18 degrees Celsius to 3 degrees Celsius, but that was still in liquid form. So it was just hot water or mildly warm water, room temperature, to colder a colder, lower temperature of 3 degrees, but it was still liquid. So we can just use the specific heat capacity equation. However, in part B, not only is there a temperature drop of 3 degrees to 0 degrees, but also additionally, we're changing state. So we've got to use two equations. This is the first equation I'm going to use, and this is the second equation. So and now there's one bit of information I forgot to jot down here. It's my mass. Now my mass hasn't changed. It's still the same 0.1 kilogram of water in the question. So although part B has not stated what the mass is, part B is part of question 4A. So you've got to still use the 0.1 kilogram of mass. Okay, so I'm going to put that here, 0.1 kilograms. So let me first of all work out the energy transferred in the first step of going from 3 to 0. So I write it out, delta E equals 0.1 times 4,200 times 3 minus 0 is 3. Should get something close to 1,260 joules. So we've worked out the energy bit for the specific heat capacity for the temperature change. Now let me work out the delta E. This is the energy required to convert liquid water into solid water, and it's the latent heat of fusion because it's freezing, isn't it? And it's this equation, so I'm just going to write out what is in that triangle there. So I cover up my E, and I'm left with M times LF. My mass is still the same, isn't it? Now my LF is given to me in the question. Let me go back to it. My LF is 340 kilojoules per kilogram. So I need to times 340 times 1,000. So let me do that. So 340 times 1,000 is that. And plug all that into your calculator. You should get 34,000 joules. We're almost there, guys. If you did everything up to this step, you get 3 out of 4 marks, okay? To get the final 4th mark, what we need to do now, we need to add these values together. It says, calculate how much energy would need to be removed from the water to cool it from 3 degrees and to freeze it. So we're told in the question, temperature has dropped and it has changed state, which means we want to work out the total energy that's been removed in this case. So let's add these two numbers together. So E total equals my 1,260 plus 34,000. And that should give you 35,260 joules. So it says estimate how long it would take to cool it from 3 degrees Celsius and freeze it. Now for this question, we've already worked out in part A, II, calculate the rate of transfer of energy from water. The answer in 4A part II was 14 joules per second. That's how long it has taken for the rate of energy transfer. Now it says how long would it take to cool. So basically, how long is this process going to take? What we would need to do is, so we're told that 35,000, so this is part 2, we're told that 35,260 joules have been taken from this liquid water, and the rate of transfer is 14 joules per second. Okay, so basically what I'm using here is delta E over delta T is my rate of energy transfer, and I want to work out this delta T because it says how long. Yeah, so rate of energy transfer equals my my energy, which is this bit, and I want to work out this. So I'm going to make delta T the subject. So delta T is equal to delta E divided by rate of energy transfer, and that's what I've got here. So delta E is on the top and rate of energy transfer is on the bottom. Do that in your calculator, 35260 over 14, and you should get, in seconds, 2,520 seconds.